بسم الله الرحمن الرحيم. الحمد لله والصلاة والسلام على رسول الله. This is Math 223 Linear Algebra, and we will use the book of Anton, Elementary of Linear Algebra with Applications, 12th edition. And let us start with Chapter 1, which is about systems of linear equations and matrices. So, Section 1.1, Introduction to Systems of Linear Equations. Whether we have linear systems in two unknowns or three unknowns. In two unknowns, like here, x and y are the variables. So the graph would be a straight line for each equation. So the two lines either parallel or intersect, or they represent one line. So we always have three possible cases for the solutions of this type of linear systems. Either no solution, or one solution, or infinitely many solutions in case of one equation or one line. The solutions in this case would be all the points of the line. Here the solution is the intersection point, and here there is no solution. There is no intersection point. These three possibilities are always there, even if we consider systems of three equations and three variables, or even if we consider systems with four equations and four variables, or more than that. Even the number of equations doesn't have to equal the number of variables. We could have two equations and four variables, for example. So always, every system of linear equations has either zero solution, no solution, or one solution, or infinitely many solutions. If it has zero solution, no solution, we call it inconsistent system. If it has one or infinitely, we call it consistent. For example, this is a linear system, and let us try to solve. We can solve it by elimination, by adding. We add the two equations and eliminate one of the variables. It is called elimination or addition method. When we add these two equations, negative y, positive y will be cancelled, and we will have 3x equals 7. So x is 7 over 3. And we can replace x in any of the two equations. For example, in the first equation, 7 minus 3 minus y equals 1. So we find that y equals 7 over 3 minus 1, or just 4 over 3. So the solution set in this case is one solution. The value of x is 7 over 3, and the value of y is 4 over 3. And this is the intersection point between the two lines, and it's a point in a plane, in the plane. While here, in this system, if we want to eliminate one of the variables, if we add, there is nothing to eliminate. But for example, if I multiply the first equation by negative 3, so I'll have negative 3x, negative 3y equals negative 12, and the other equation as it is. Now, if I add the two equations together, I'll have 0 in the left-hand side and negative 6 in the right-hand side. And this statement is false statement. It's not a correct statement. And this means that if you replace x and y by any numbers, you will always end up with a false statement. So this means that the system has no solution. So the solution set is phi, or you say the system has no solution, or you say the system is inconsistent. While in this case, to eliminate one of the variables, I have 4 and 16, so I'll multiply the first equation by -4. So negative 16x, -4 times -2 is positive 8, -4. And here I have 16x minus 8y equals 4. Now, if you add the two equations in the left-hand side, I'll have 0 because 16 cancels with -16 and 8 cancels with -8. And here -4 plus 4 is 0. 0 equals to 0 is a true statement. And it means that the two equations are similar, are equal, the same equation. So actually, I have one equation in this system, one equation in two variables. So there is no unique solution. I have infinitely many solutions. To represent the solution set, uh, I can say I can solve the first equation for x, for example. So 4x would be equal to 2y plus 1, and then x would be equal to 2 over 4. 2 over 4 is just 1 over 2 plus 1 over 4. And I can call y t, so let y equals t, where t is any parameter, and x would be equal to half t plus 1 over 4, and t belongs to R. T is any real number. So the solution set consists of all ordered pairs x and y uh, like this. Y is t and x is half t plus 1 over 4. So for example, if you want to find some solutions of this system, replace t by any number. So if you put t 0, for example, then x would be 1 over 4. So this is one of the solutions. If you put t1, for example, notice that t is y. So x would be half plus 1 over 4. That's 3 over 4. If you put t -2, for example, then we will have half times -2, that's -1, plus 1 over 4, that's -3 over 4. So you can have as many solutions as you wish. We have infinitely many solutions, but all the solutions are written in this form. If you want, you can say that the solution set consists of all ordered pairs, where x is half t plus 1 over 4, and y is t, and t belongs to R. So it consists of all such ordered pairs, which are really the points of the line, the points of this line, 4x minus 2y equals 1. The two equations, remember the two equations are the same, exactly the same. Another example of a linear system with infinitely many solutions. If you look carefully to the three equations, you will notice that if we multiply the first equation by 2, I'll get the second equation. And if I multiply the first equation by 3, I'll get the third equation. So in fact, I have only one equation, which is the first equation. The other two equations are the same first equation, but multiplied by a constant. So this doesn't change the equation. Remember, if x equals to 2, and you say 2x equals to 4, this is the same equation. You don't get any new information here. X is 2 here, x is 2 also below in the second equation, and so on. So if you multiply an equation by a constant, this doesn't change, doesn't give you a new equation. So in fact, I have only one equation. So one equation and three variables, I'll have infinitely many solutions. What are the solutions? The points of this line. How to write the answer? We will always follow this method, and we will solve the first equation for one of the variables, usually the first one, x, for example, and x would be equal to 5. If you take y to the other side, it will be plus y and -2z. And then y and z are free variables. So we can call y t1, for example, and z t2, and then x would be equal to 5 plus t1 minus 2t2, where t1 and t2 are any real numbers. So again here, I have infinitely many solutions, but not any solutions, the solutions that satisfy these three equations, three conditions, okay? So again, if you want to find some examples for the solutions, some of the solutions, choose a value for T1 and choose a value for T2. So if you choose T1 and T2 zeros, so remember that T1 is Y, T2 is Z, and then find X. X would be 5. So this is one of the solutions. If you take T1 1, T2 negative 1, then X would be what? 5 plus 1, 6, minus 2 times negative 1, so plus 2, so that's 8, and so on. You can find as many solutions as you like, all points, all ordered triples in this case, in the space satisfying these conditions would be solutions of the system. Now let us introduce what we know by what we call augmented matrix for a system. Augmented matrix for a system. What is the augmented matrix? If I have a system like this would be the augmented matrix. How can I get it? Well, the first equation, I write the coefficients 1, 1, 2, and then 9, the constant term. But the equation has to be written like this. The numbers are on the right-hand side, and the variables are on the left-hand side, and so on. This is the second equation, the third equation. And you can say that the first column represents the coefficients of the first variable, x1, in all of the three equations. So 1, 2, 3. And the coefficients of x2 are represented by column 2, 1, 4, 6. And these are the coefficients of x3, 2, negative 3, negative 5, and 9, 1, 0 are the constants in the right-hand side. So we start by representing the system by the augmented matrix, and then we work with this augmented matrix to solve the system by methods called Gaussian elimination or Gauss and Jordan. We use row operations. We use what we call elementary row operations. There are 3 row operations. First, multiply a row by a non-zero constant. So you can multiply any row by any number you like. For example, 2R1 or half R2. When you say R3 over 3, for example, you are multiplying R3 by 1 over 3. So you can say that. So this is the first type of row operations. We use this to change to 1, to change to 1. Whenever I need to change a number to 1, I can just divide by 3 or 2 to make it 1. Interchanging any two rows, and we represent this by writing R1 if and only if R2. So I mean interchange row 1 with row 2. Okay, and also we use this second row operation to change to 1. If we want to change a number to 1, we use also the first or the second row operations. The third one is used only to change to zeros, okay? Add a constant time one row to another. So for example, I have 1, 2, 3 here. If I want to make this 2 0, what should I do? I multiply the first row by negative 2 and add to row 2 and change row 2 by the result by this transformation. So add a constant. The constant is -2 times one row, which is row1 here, to another, which is R2. This method will change numbers to zeros. So whenever you want to change to zeros, use the third row operation. These are the only possible row operations in which you use them with the augmented matrix and do not change the solution of the system. Okay, if you use any other, if you invent a row operation by yourself, it will change the solution and your solution will not be correct. So let us have a look to this example. This is a system and the question solved. I will solve it by what we call Gaussian elimination, and we will study this method in section 1.2. So the first step is to write the augmented matrix of the system. So the coefficients of x, 1, 2, 3, and the coefficients of y, I have 1, 4, and 6, and the coefficients of z, 2, -3, and -5, and the constants. I can add this vertical bar to differentiate between the left-hand side and right-hand side. You can write it or you don't have to write it. It's up to you. So the Gaussian elimination says that the first number, this number should be 1 in the augmented matrix. Then use this one to make these numbers zeros. Now you finished from the first column. The second column, make this number 1. And then make this number 1 and make it is 1 already, so make the number below it 0. And then the first column is finished. The second column is finished. Now make this number 1. This will be the last step in Gaussian elimination method. So let us apply this method. I have 1 here in the first row, first column. So that's good. If I don't have 1, I should use one of these 2 row operations. If it is 4, for example, I can divide row 1 by 4. Or if it is 4 and I have 1 below it, I can interchange the 2 rows and have 1 always here in the first place. We call these 3 ones are called the leading ones in each column. So this is the leading one in the first column, and I will use it to make 2 and 3 zeros because I have 1 here. So the next step is to make these numbers zeros. How? I use the third row operation. So if I multiply the first row by -2, so -2R1, and add that to row 2, I'll get 0 here. And I will replace R2 by this transformation or operation. And the 3, I can make it 0 also using this one by multiplying the 1 in row 1 by 3 and add it to row 3. Now I will have a new matrix, but with the same solution of the system. The solution of the system will not change. Here I am not changing row 1, but I'm changing row 2 with this operation. So -2 times 1 is -2 plus 2, that's 0. -2 times 1 is -2 plus 4, that's 2. -2 times 2 is -4 plus -3, that's -7. -2 times 9 is -18 plus 1, that's -17. So this is row 2. Now row 3, I will use this operation. -3 times 1 plus 3, that's 0. -3 times 1 is -3 plus 6, that's 3. -3 times 2 is -6. plus minus 5, that's negative 11. Negative 3 times 9 is negative 27 plus 0. So now I finished from the first column. It is 1, 0, 0. So I go to the next column, and this 2 has to be 0. Has to be 1. How can I make it 1? Either I divide the second row by 2 to make it 1, or I look to the row below, row 3. If this number, the 3, is 1, or it's easier to change it to 1 than this one, then I will interchange row 2 and row 3. But I noticed that it is the same. This is a 3, and it's not easy to change it to 1. I'll have fractions. Also here I'll have fractions, so I will divide row 2 by 2. This is the first operation. Okay? So the new matrix would be 1, 1, 2, 9. There is no change. And here I have 0, and now I have 1. And negative 7 over 2, and negative 17 over 2. So I finished from this one. I made 1. I have a leading 1 now in column 2. Leading 1 in column 2. This is called the leading 1 in column 2. I use it to make the number below 0. Well, the number below is 3. So I'll multiply this number, which is 1, by negative 3. So negative 3 row 2 plus row 3. You can't use this one to change the 3 to 0. If you use this one, then this 0 will change. Okay? So please just follow these steps. This is the Gaussian method. Please follow the steps and you will always get the correct answer if you don't do any mistakes in calculations. So the new matrix would be 1, 1, 2, and 9. There is no change. And 0, 1, negative 7 over 2, negative 17 over 2. There is no change. And now I have 0. Negative 3 plus 3 would be 0. So this is 0. And negative 3 times negative 7 over 2 is 21 over 2. You can use the calculator if you like. 21 over 2 minus 11. So this will give you negative half. And negative 3 times negative 17 over 2, this is 51 over 2 minus 27, and this will give you negative 3 over 2. So now I finished from the second column. I have 1, 0. So the last step in Gaussian elimination is to make this number 1 in the third column, and it is the leading one. It would be the leading one. I have negative half. What to do to make negative half 1? I multiply by negative 2. So if I multiply row 3 by negative 2, I'll have this matrix 1, 1, 2, 9, and here 0, 1, negative 7 over 2 without change, and negative 17 over 2, and here 0, 0. Negative 2 times negative half, that's 1, and negative 2 times negative 3 over 2, that's 3. If you are using Gaussian elimination, that's it. We stop here. And we write the system of equations again, okay? So if you have a system of equation, you can write the augmented matrix. And if you have the augmented matrix, you can write the system. Remember, this is X. These are the first column represents the coefficients of X, and this is Y, and this is Z. So the first equation would be X plus Y plus 2Z equals 9. Second equation would be Y minus 7 over 2Z equals negative 17 over 2. And the third equation, Z equals to 3. So from the third equation, I have the value of Z. I use a method called back substitution. I go back and substitute. So if I go back to the second equation now, I have y minus 7 over 2 times z, but z is 3, so I can replace z by 3. So I have y minus 21 over 2 equals negative 17 over 2. Now, if I take negative 21 over 2 to the other side, it would be negative 17 plus 21 over 2 would be 4 over 2, which is 2, so y is 2. Now I go to the first equation, go back to the first equation. X is unknown. I know now that y is 2. I know that z is 3, so 2 times 3 is 6 equals 9. 6 plus 2 is 8. Take it to the other side, I'll have 9 minus 8, that's 1. So these are the values of the variables. So you can write the solution set as the value of x is 1, the value of y is 2, the value of z is 3. I have one solution for this system, which is 1, 2, 3. Find the system of linear equations in the unknowns. So this is an augmented matrix, okay? So there is a line here, and we can write the first equation. X1 has coefficient 0, so 3x2 minus x3 minus x4 equals negative 1. And 5x1 plus 2x2, x3 has coefficient 0, minus 3x4 is negative 6. So this is the system of linear equations that's represented by or corresponds to this augmented matrix. Solve the linear system if possible and use the result to determine whether the lines represented by the equation have 0, 1, or infinitely many intersections. If infinitely many, find parametric equations for them. Parametric equations are the equations we found here, like this. This is called parametric equations because T1 and T2 are parameters. So let us start with the first equation. Let us solve by elimination. 3 and 6. So let me multiply the first equation by negative 2. So I'll have negative 6 plus 4y, negative 2 times 4 is negative 8. And here I have 6x minus 4y equals 9. Add the two equations together. I'll have 0 equals to 1. This is a false statement, so the system has no solution. It is inconsistent. Also, I will multiply the first equation by negative 2 and the second equation as it is. Add the two equations together. I have 0 equals to 0. So here I have infinitely many solutions. How to write the parametric equations? Well, solve the first equation for x. Divide by 2. 2 over 4. Sorry, if you divide by 2, 4 over 2 is 2. So this is the first equation, 2x equals 4y plus 1 divided by 2. I have 4 over 2 to y1, that's it. Then now call y t, then x would be 2t plus half, where t is any real number. So these are the parametric equations. Use parametric equations to describe the solution set of the linear equation. I have 1, 2, 3, 4, 5 variables here, 5 unknowns in one equation. So of course, there are infinitely many solutions. We'll solve this equation for one of the variables, okay? Well, I can solve it for v, for example, but it's easier for me to solve it for y here. So if you take y to the other side, then y would be equal to 3v minus 8w plus 2x plus 4z. So the parametric equations here would be v, I'll call it t1, for example. W, I'll call it t2. X, I'll call it t3. Z, I'll call it T4, and Y would be 3V, but V is T1 minus 8W, but W is T2 plus 2X, but X is T3 plus 4Z, but Z is T4. So these are the parametric equations, and you can say that all of these parameters, the four parameters, are real numbers. Well, uh, this is the end of section 1.1. There are many exercises you can practice, but these are the main ideas